Okay, this is 8.4, relationships among the functions, and today's objective will be to simplify trigonometric expressions and to prove trigonometric identities. This is some of my favorite stuff in trigonometry. Trig proofs are out of this world, and you guys are going to be amazed at what you're going to be able to prove very shortly. It's going to take a little work on your part, but you can do it. So, first off, let's talk about some things like some identities, the reciprocal relationships. Now, I am hoping that you guys remember that cosecant of theta is 1 over sine of theta. That's called a reciprocal relationship. It could also be written sine of theta is 1 over cosecant of theta. All right? Now, secant of theta is 1 over cosine of theta, which implies cosine of theta would also equal 1 over secant of theta. And then cotangent of theta would be 1 over tangent of theta, which also implies tangent of theta would have to equal 1 over cotangent of theta. So pretty powerful, and we use these a lot. Okay, now relationships with negatives. Notice how I set up this little definition right here, okay? I have 4 trig functions on the left and 2 trig functions on the right. And my input is the opposite of theta for each of these. All right, and that's what they mean, relationships with negatives. Now here's how this works. The functions on the left are all odd functions. And what I mean is that the definition of an odd function is f of negative x will always equal the opposite of f of x. And here's why. Let's focus on sine. Okay, remember our friend the unit circle right here? All right, and let's say we have this angle right here with the terminal point xy. Well, sine of this angle would be y. Now, if I took the opposite of that angle, then sine of the opposite of angle would be the opposite of y. And so, with relationships with negatives, sine of negative theta will always equal the opposite of sine of theta. Simple as that. And that is because of this little diagram right here. Now that also is going to work with our other odd functions, cosecant, tangent, and cotangent. So cosecant of negative theta is the opposite of cosecant of theta. Tangent of negative theta is the opposite of tangent of theta. And cotangent of negative theta is the opposite of cotangent of theta. And, you know, if you ever see like an input of the opposite of theta, you will probably want to rewrite that in terms of theta. Now, over here, cosine and secant are even functions. That implies they have symmetry with the y-axis, all right? So here's what's going on here. Let's see if I can explain this with this circle right here, okay? So, yeah, cosine. Well, cosine of theta would be this horizontal distance right there, or x. And cosine of the opposite of theta would be the same horizontal distance right there. So the relationships with negatives for even functions would be this. And the definition of an even function is f of negative x equals f of x. So cosine of negative theta would always equal cosine of theta. And secant of negative theta will equal secant of theta. There you have it. Pretty powerful stuff right there. Okay, now the Pythagorean relationships. All right, now I can't remember. I don't know if we've talked about these yet, but you're going to use these a lot, especially when you're simplifying trigonometric expressions or you're proving trigonometric identities. A lot of people will call this very first one right here the most important identity in all of trigonometry. Supposedly with this identity, you can prove anything. So here it is. Sine squared of theta plus cos squared of theta equals, and whenever I see sine squared plus cos squared, I get very excited because I know sine squared of theta plus cos squared of theta will always equal 1. And admit it, 1 is much simpler than sine squared plus cos squared. Now, 1 plus tangent squared of theta will always equal secant squared of theta. And we'll prove some of these down the road and maybe today. And then 1 plus cotangent squared of theta, well, that's going to equal cosecant squared of theta. All right, so you're going to use these a lot, and you're going to manipulate these to use them in different forms. All right, really good stuff. Now, let's go here. Let's talk about cofunctions. Have you ever thought, what's the deal with sine and then cosine, tangent, cotangent, secant, cosecant? Those are called cofunctions. And here is what this is about right here. Everybody take out your calculator and punch out sine of 50 degrees. So make sure you're in degree mode. I'm in radians right now, so I'm going to change that to degree mode. And now, let me clear my screen. And sine of 50 degrees. What does sine of 50 degrees equal? This is not going to be pretty. It is 0.766. Hey, now sine of 50 degrees, yeah, 0.76604444431. All right, now I'm sure I rounded that. How about 0.766? I like that a lot. Now guess what? I already know what cosine of 40 degrees is then. All right, but here's what I'm thinking right here. Sine and cosine are cofunctions, and 50 and 40 are complicated. 50 and 40 are, what do you call, complementary angles. Wow, I'm getting old. All right, so guess what? When you punch out cosine of 40 degrees, let's discover something right now really exciting. Cosine of 40 degrees is the same thing, approximately 0.766. And that's going to work out every time here. So let's go sine of 25 degrees, sine of 25 degrees, approximately 0.423. All right, and note the cofunctions, note the complementary angles. Guess what's going to happen when you punch out cosine of 65 degrees? Let's check that. And guess what? Your conjecture was correct. That would be 0.423 approximately as well. Now, we'll do it 2 more times. Cosine and sine, those are cofunctions. 11 and 79, those are complementary angles. All right, so if I know cosine of 11 degrees, I know sine of 79 degrees. So cosine of 11 degrees, and I'm getting approximately 0.982. All right, and I already know 0.982, but let's have our calculator confirm that. So sine of 79 degrees, and sure enough, approximately 0.982. D, note the cofunctions, sine and cosine. Note the complementary angles, 83 degrees and 7 degrees. So what is sine of 83 degrees? Sine of 83 degrees is approximately 0.993. Okay? Now, conjecture. What is cosine of 70 degrees? I hope you are thinking 0.993. And let's punch that out just to double check. So cosine of 7 degrees is, and look at that, approximately 0.993. So let's work on our identity. Sine of 18 degrees would have to equal cosine of the complement of 18 degrees, which would be 90 minus 18 degrees. Cosine of 89 degrees would have to be equal to sine of the complement of 89 degrees, which would be sine of 90 minus 89 degrees. And I know you're thinking, Gibbons, why did you write the complement of 18 as 90 minus 18? Why did you write the complement of 89 as 90 minus 89? We all know that's 1, and we all know that's what, 72? All right, because I want to go to an identity. So gee, what would sine of theta be? Well, sine of theta would be equal to cosine of 90 minus theta. So what you're typically going to do is you're going to see this in an expression that you have to simplify, or in an identity that you have to prove, and you're going to rewrite it as sine of theta. Same thing here. Cosine of theta will equal sine of, that's right, 90 minus theta. All right. So this leads to our next slide, which is the cofunction relationships that we just developed. So sine of theta is cosine of 90 minus theta. And what I'm doing is a function of theta is the cofunction of the complement of theta. So the cofunction of sine is cosine, and the complement of theta would be 90 minus theta. That's how that works. All right, now where did I go? Cosine or tangent? Okay, I'm working across, so let me verbalize this first. So then cosine of theta would be sine of 90 minus theta. Tangent of theta would be cotangent of 90 minus theta. And cotangent of theta would be tangent of 90 minus theta. And secant of theta would be cosecant of 90 minus theta. And cosecant of theta would be secant of 90 minus theta. Now again, you're typically working these from the more complicated side to the simplified side. Okay? When we're doing proofs, we want to be able to simplify. All right, now let's discover something. 1 plus tangent squared of x. Okay? Now I hope that looks familiar to you. All right, but I'm not going to go back because I think it's a couple slides back. But if I graph 1 plus tangent squared of x, I'm going to get a graph that doesn't look so familiar, but we will play with it. So there it is, 1 plus tangent squared of x. So let's all do this. I hit the button before I had you punch it out, but let's double check my picture here. So let's go to radian mode, and I need to highlight radians. I was in degrees, and then I'm going to go y equals, clear everything I got. So y sub 1 is going to be 1 plus tangent, and here's how you have to put tangent squared of x in your calculator. You go tangent of x and you square that. Tangent of x squared. Okay, now let's just do this on a typical trig window now. So we'll go zoom, and do you see 7? Zoom trig. Hit that, and you've got that graph right there. And that, I'm looking at exactly the same graph I see on my PowerPoint right now. Now, I know this graph isn't familiar to you, but I want you to think about your Pythagorean identities. 1 plus tangent squared of x. Didn't we just say that 1 plus tangent squared of x was equal to secant squared of x? So now, let's graph y equals secant squared of x. All right. Now, how are you going to put secant squared into your calculator? Because I don't see a secant button, do you? But here's what I'm going to do. How about I put this in as y sub 2, and then I hope that my graph of secant squared of x will just come right on top of that graph of 1 plus tangent squared of x. All right. So secant, what was the reciprocal relationships we were just talking about? Isn't secant 1 over cosine? So that would mean secant squared would be 1 over cos squared. So on my calculator, I'm going to go parenthesis 1 divided by cosine of x, and then I'm going to close my parentheses, all right, and I have to square that. So I'm squaring the rational expression 1 over cosine. Okay, now I think I have that all in right. Now if I hit graph this time, and look at that, my secant squared exactly the previous graph of 1 plus tangent squared. So I get the same thing, all right? Now, what does that mean? Well, we've just shown on a calculator the Pythagorean identity that 1 plus tangent squared of x equals secant squared of x. So look what they're going to say right here. B, does 1 plus tangent squared of x equal secant squared of x? Why, yes, it does. That's an identity. That is a Pythagorean identity. All right. Now, graph y equals sine of 2x and y equals 2 sine of x. Now, we've already studied amplitude and period, and these are both sine waves right here, but this has an amplitude of 1 and a period of 2 pi divided by 2, while this one has an amplitude of 2 and a period of 2 pi. So those definitely will not be the same graph. So how about we do this? Let's put them on the same graph together at one time. So I'm going to go y equals, and y sub 1 is going to be, let me clear what I have there. So y sub 1, make sure you do this with me, is sine of 2x. And then y sub 2 would be 2 times sine of x. And, you know, there will be different colors on your fancy graphs. On my older calculator that I did this on, I'm going to make the second one bold, and here's what I have. Obviously, those are not the same graph. So sine of 2x does not equal 2 sine of x. And look at what part D says. Is sine of 2x equal to 2 sine of x an identity? Obviously not. Those are not the same graph. No. All right, E. Graph y equals secant minus sine of x times tangent of x. And remember, to do this, we're going to need our reciprocal relationships, because I don't know about you, but my calculator does not have a secant button. So let me clear what I have there. And I'm going to go y sub 1 is secant. I'm going to write that as 1 divided by cosine of x. And then minus, and I do have a sine of x, times, and I do have a tangent of x. Oh, I wonder what this graph is going to look like. Secant x minus sine of x times tangent of x. I don't know what that's going to look like, you guys. But let's do that on our typical trig window. So go zoom, trig. And here it comes. I know it's not on the PowerPoint yet, but I'm looking at it on my calculator. And I don't know about you, but I am getting excited. Do you recognize this graph? No, we're starting at 1. And I'll bet you this is pi over 2, pi, 3 pi over 2, and 2 pi. That looks like cosine. Yeah, I'm excited. All right, so let's think about this a second though. First, what is the domain of secant, sine, and tangent? Well, sine, the domain is all real numbers, okay? But secant, remember your reciprocal relations. Secant is 1 over cosine. And tangent, by the way, is sine over cosine. That means secant and tangent are not defined whenever cosine equals 0, which would be first at that pi over 2 right there. Yeah, x cannot equal pi over 2. And then here we go, what? 3 pi over 2? And I could go the other way. negative pi over 2, negative 3 pi over 2, and forever in both directions. So I'm going to write this. What is the domain of secant and tangent? Well, x cannot equal pi over 2 plus, and what is this distance between these asymptotes I put into this graph? That would be pi units, so plus any multiple of pi. All right. So your graph does not show the holes that are here, but trust me, there are holes whenever that graph is intersecting the x-axis. Therefore, those x-intercepts actually don't exist. And that's just one pixel on a calculator that is not lighting up. So your calculator, no matter how far you zoom in, won't show you those holes. So I really exaggerated them right there. Okay? But do you guys agree that looks a lot like cosine other than those holes? So, on the same set of axes, graph y equals cosine of x. So I'm just going to go to my calculator, and I'm going to go at y sub 2, I'm going to go cosine of x, and I'm betting I get the same graph, and my holes will just be covered now. So I'm going to hit graph, and here it comes on my newer calculator in red, and exactly what I thought would happen. There it is right there. There's cosine of x. Okay? So, what is the domain of cosine? Well, the domain of cosine is all real numbers. So I'm going to say x is in the set of real numbers. So now, what we have if we do a domain restriction is we have another identity. I could say cosine is equal to secant of x minus sine of x times tangent of x, as long as we restricted the domain to x can be any real number other than pi over 2 plus any multiple of pi. All right? And you guys, this is how mathematicians way back in the day created these types of identities. All right? I wonder if they're going to have us prove this today. Simplify. So, if we simplify secant of x minus sine of x times tangent of x, take a look here. Shouldn't that simplify to cosine of x? Well, let's find out. Okay? Now, I've mentioned the reciprocal relationships several times today. Showed them to you once too. So let's take a look at those again. If I'm going to simplify this, all right, I'm going to start off with, see that secant? 1 over cosine. Agreed? Minus, and sine I'm going to leave alone. All right? Oh, I should have brought this in first, by the way. And here it is right here. Do you see this? Secant of theta equals 1 over cosine of theta. So there we go. Secant of x is 1 over cosine of x right there. And now the sine of x, we love sine. Let's leave that alone. Now tangent, many times what we will do is write our trig functions in terms of sine and cosine. And you guys know that tangent of x is sine of x over cosine of x. And the reason I'm going to do that is because now I have two terms with a common denominator. So it's going to be easy for me to simplify. Equals, let's put these over the common denominator of cosine. And what's that going to give me for my numerator then? 1 minus sine times sine, which is 1 minus sine squared. And you might be thinking right now, Gibbons, how did that help? That's not looking so much better. But then go back to your Pythagorean identities. The Pythagorean relationships right here. That 1 minus sine squared? Well, here we go. Do you see the sine squared theta plus cos squared theta equals 1? Doesn't that mean that I could solve this for cos squared theta? And wouldn't cos squared theta equal, let's subtract sine squared from both sides, 1 minus sine squared. Okay, now I'm using x's here because we're using x's over here in this expression. All right, but anyway, so I'm going to rewrite 1 minus sine squared of x as cos squared of x. And then I have factors that cancel. So cos squared of x over cosine of x would equal cosine of x. And that's pretty simple right there. So secant of x minus sine of x times tangent of x equals cosine of x. Okay? as long as we have the restricted domain of that x cannot equal pi over 2 plus n pi that we saw in the previous slide. Beautiful. Okay, now we're going to do our first trig proof. Wow, and they're not going to start us off with anything easy, not in this curriculum. They're going to throw something like cotangent of A plus times 1 plus tangent squared of A over tangent A equals cosecant squared A. Now, when you are asked to do a proof, what you want to do is pick the more complicated side and see if you could simplify that to get to the simpler side. So what I'm going to do is I'm hoping I can manipulate this left-hand side. Okay? So my first thought would be this. 1 plus tangent squared of A. Now, is that not one of our Pythagorean relationships? 1 plus tangent squared of theta has to equal secant squared of theta. So I'm going to take this parenthesis and bam, 1 plus tangent squared of A, I can write as secant squared of A. Okay, there's my first step. And the thing about a trig proof is, as long as you're using identities, you're going to get the correct answer. You're going to prove what needs to be proven. Now, some of us will take a few more steps than others. That's okay. I remember my prof in college, I'd do a proof in like 8 steps, and then he would look at me and say, hey, that's great, Mike, but we could have been a little more concise, and he'd do the same proof in like 3 steps. All right, but that's how I learned. All right, now where am I going to go? Well, you know what? Cotangent and tangent, aren't those cofunctions? Okay. And doesn't tangent equal 1 over cotangent? So see this tangent right here? What if I thought about that as 1 over cotangent? Okay. And where do I have it? It's written here as cotangent of theta equals 1 over tangent of theta. But doesn't that imply that tangent of theta would have to equal 1 over cotangent of theta? And if I'm dividing by 1 over cotangent, isn't that the same as multiplying by cotangent? So I'm going to go cotangent of A over tangent of A is cotangent squared of A. And then I'm going to leave that secant squared of A alone for a moment. All right? Now, I could have done this step too right now, but I want to take baby steps here. That's probably why my prof would do these proofs in 3 steps, and I took a few more. All right? But I'm getting better. All right, now let's think about this. All right, cotangent and secant squared. All right, well, isn't like secant 1 over cosine, and cotangent is cosine over sine? So I can go back to that thing I mentioned earlier in this lesson. Sometimes we just have to simply rewrite things in terms of sine and cosine. So let's write everything in terms of sine and cosine and watch what happens here. All right, so cotangent squared of A, well, cotangent is cosine over sine, so cotangent squared of A would be cos squared of A over sine squared of A. All right, that's that first factor right there. Now you're thinking, Gibbons, you just made that a little more complicated. Why did you do that? Because the same thing here. Secant of A is 1 over cosine of A. So secant squared of A would be 1 over cos squared of A. And look at, by doing that, do you guys see that the factors of cos squared of A would cancel out? Leaving us 1 over sine squared of A. And then, again, 1 over sine squared of A. Think about those reciprocal relationships. Isn't sine 1 over cosecant? Do I have that up here? No, it's written this way. Cosecant of theta equals 1 over sine of theta. But that implies sine of theta would equal 1 over cosecant of theta. So this sine squared in a denominator is 1 over cosecant squared. And if I'm dividing by 1 over cosecant squared of A, aren't I multiplying by cosecant squared of A? So I'm going to go equals cosecant squared of A. And look at that. Isn't that what I was trying to prove? So we just proved a really ugly identity. We have just proven that cotangent of A times the quantity 1 plus tangent squared of A, and all of that divided by tangent of A equals cosecant squared of A. And that, my friends, is your first proof. And when you complete a proof at the University of Washington, you have to tell University of Portland. All right, I took some classes at Washington, but I graduated from Portland. You got to tell Brother Bill Fuller, quod erat demonstrandum, as was to be demonstrated. All right, and guess what? I threw a lot at you today. All right, and I'm going to give you some problems. And these problems are simplifying trigonometric expressions and then some trigonometric proofs. And I might even put a video in the Google Classroom that shows you how I would handle these problems, but I want to let you play with them a little bit on your own. And it's going to be tough. It takes a while to master simplifying trigonometric equations or expressions and proving trigonometric identities. But it gets easier and easier and easier. And pretty soon you're going to feel like you're a master at doing trig proofs, I promise you. All right? You guys, do your best on those problems, all right? And email me if you need a little extra help. All right? Everybody have a great day.